Hello, and welcome back to Physics 123, Quantum Mechanics 1. So far, we have discussed about the uncertainty principle in X and P in the previous chapters. So, the uncertainty in position and momentum must actually be greater than or equal to h bar over 2. So, even though h bar is a very small quantity, 10 to the negative 34, so in classical mechanics, this is essentially zero. You can uh, measure both position and momentum at the same time. But in quantum mechanics, h bar is a very large quantity. Therefore, you cannot measure both position and momentum at the same time, because if you have uh, small certainty or uh, small uncertainty rather in position, you will have a large uncertainty in momentum and vice versa. So we also have discussed about a commutation relation between two operators. So if there are two operators A and B, so if they're placed in a notation similar to this, then this means that AB minus BA. So if the two commutes, then AB minus BA are just the same, equal to, meaning AB minus BA is equal to 0. But if A and B does not commute, then AB is not the same as BA. Take note that in quantum mechanics, we represent operators as Hermitian matrices. So for this lesson, similar with what we did in the previous lessons for this chapter, we are trying to generalize the concepts in quantum mechanics. So now we will generalize the uncertainty principle. So this is now the generalized uncertainty principle for any two operators A and B. So the uncertainty in operator A squared multiplied by the uncertainty in operator B squared is must be greater than or equal to this term here. So the brackets represent expectation value. So expectation value of the commutation relation of A and B. Again, this is the meaning of the commutation relation between A and B. So if you have operators that commute, meaning they are compatible with each other, they will share the same eigenfunction. So for instance, the Hamiltonian commutes with the angular momentum, the z component of the angular momentum, meaning the angular momentum and the z component, one of its components, say the z component, will actually commute with each other. So what does this mean? So meaning the Hamiltonian and, for instance, the angular momentum operator will have the same eigenfunctions psi n, even though they have different eigenvalues. Because for the Hamiltonian, the eigenvalue is energy, and of course for the angular momentum, the eigenvalue is angular momentum, which is a function of h bar. Take note, h bar as the unit of angular momentum. So for incompatible observables, a second measurement will render the outcome of the first measurement obsolete, meaning you cannot simultaneously measure both of the observables at the same time. So for instance, we try to verify the uncertainty relation in position and momentum. So the commutation relation between X and P is actually IH bar. This term here in the commutation relation, this is IH bar. So that you will obtain the uncertainty relation in position and momentum. We can also have an uncertainty principle with respect to energy and time. And we start, we can have that principle by first calculating the time rate of change of the expectation value of an observable or physical quantity Q. So in general, given by this, so this is the commutation relation of your observable with the Hamiltonian, with the total energy operator. And this is just, it's a partial derivative. So if Q does not explicitly depend on time, so most of the time this is 0. So for the uncertainty in time and energy, we can, from using this and the generalized uncertainty principle, we can arrive at the uncertainty principle in time and energy, or in energy and time. So sometimes we, instead of using the sigma notation for uncertainty, we use delta. They're just basically the same. So these two notations are basically the same. So meaning, what does this mean? You cannot measure the energy precisely if you are given a lot of time, or you cannot measure the energy precisely. You will have a large uncertainty in measuring the energy if your time is very limited, or it's very short. Short time means uncertain energy. Long time, so a large change in time will result in a small or accurate measurement of the energy. So actually this is very much applicable in particle physics, when particle physicists measure the energy of a particle. Okay. Another interpretation is, if the time of measurement is short, the energy values will have a wide range. So your energy will be uncertain. So example, let's have some examples. So prove that, so this is just an example for commutation relation. I think this is just very easy. To prove that AB, the commutation relation of the operator combining AB and C is this one. So from our notation, this is actually just AB times C minus C times AB. So I can actually add a middle term here. So minus ACB plus ACB minus CAB. So I added a middle term here. And then I group these two. So you will have ABC minus CB plus you will have AC minus CA, a factor of the B on this side here. So BC minus CB is just the commutation relation of B and C. AC minus CA is just the commutation relation of A and C. Okay, so quite easily done. QED. Next example. So show that the commutation relation of the position operator raised to the power of n and the momentum is IH bar n x to the n minus 1. Okay. So in this case, we need to act these operators on a test function. So take note that the momentum operator in position space is h bar over I d dx, the first differential operator, first derivative operator. So we will try to act these functions or operators on a test function g. So basically, I will just take out the constants for p, h bar over I, since these are not operator, and the operator is just x to the n, and then d dx acting on g. So what does this mean? So this means that you have h bar over I. So In the first, the meaning of this is xn times ddx acting on g. So the derivative acts first on g, then multiplied by x to the n. Minus, the second is ddx of the xn, then first acts on g, then take the derivative. So ddx of xn g. Okay, so you have h bar over I, x to the n, dg dx, and derivative of that with respect to x. So g is a function of, we'll assume that g is a function of x. So this is a product. So you will have x to the n dg dx plus g, derivative of x to the n with respect to x, which is just n x to the n minus 1. So these two terms here will actually cancel each other out. And what we get is negative h bar over I n x to the n minus 1 times g. So basically, this term here, the result of our commutation relation for x to the n. So this is x to the n of p acting on g. I can actually rationalize this, multiply by I, and then I. So I squared is negative 1, and negative 1 will cancel each other out, and it's just equal to I h bar. Quite easily done, QED. Okay, next example. So I will just leave this example to you, since these are just very easy examples. Again, you need to let this act on a test function. So say g, you let it act on a test function g, and do what we did in the previous examples. I'm just going to leave this to you. So this is now an example of energy time uncertainty principle. So the plot shows the rest mass distribution for delta particles, which have a lifetime of 10 to the negative 23 seconds. So these delta particles are very, very short-lived. Their lifetime is just 10 to the negative 23 seconds. Very much faster than the blink of an eye. Actually, if you blink one time, maybe many delta particles have already died by just blinking. Okay, so the particle physicists measured the rest mass of delta functions. So they measured the mass of the delta function and then plotted it versus the count. How many delta functions have this value of mass? So by the way, in particle physics, from Einstein's equation of E is equal to mc squared, m here is what we call the rest mass, your mass when you are not moving. That is why rest mass can actually be written as E over c squared. So essentially, mass and energy are the same because the proportionality constant is just c squared. It's just a constant. So essentially, mass and energy are basically the same. So basically, in terms of energy over c squared, you write, particle physicists write the mass of particles as energy per unit of c squared. So this is the result of the plot of the rest mass distribution for delta particles. So most of the particles have values or have an average value of 1,232 mega electron volt per c squared, and with a standard deviation of 60 mega electron volts per c squared. So the question now is, why does the rest mass sometimes higher or lower than the peak rest mass? And does this violate the energy time uncertainty principle? So why does delta particles have varied rest mass in the first place? Okay, so from the uncertainty in energy and time, you notice that if the time is, if delta t is small, these two are inversely proportional with each other. You can cross multiply this to show that they're inversely proportional. So if the delta t is small, meaning delta E is large. So if the lifespan of a particle is very short, meaning its energy is actually very large, and it will have a wide range of energies. And having a wide range of energies means you will also have, having wide range of energies means you also have a wide range of masses. So you cannot accurately measure the mass of the delta particle because its lifetime is very, very short. So, but does this violate the energy time uncertainty principle? That's the question. Okay, so delta E here is just given by this value, sigma. This is actually our delta M. So to solve for delta E just delta M multiplied by C squared. So delta M is 60 mega electron volt times C squared. So therefore delta E is just 60 mega electron volts. So multiply that by C squared. The time is 10 to the negative 23 seconds. And the question now is this greater than or equal to h bar over 2? Okay. So h bar over 2 is approximately 3 times 10 to the negative 22 mega electron volt second. That's the approximate value of h bar over 2. And this value is actually 6 times 10 to the negative 22 mega electron volt second. So it doesn't violate the energy time uncertainty principle. Where 6 times 10 to the negative 22 is definitely greater than 3 times 10 to the negative 22. 6 is greater than 3. So it doesn't violate. It is allowed by the uncertainty principle. So the uncertainty in mass is allowed due to the fact that it has a very short lifetime. Of course, if you have particles which have a very long lifetime, then you can accurately measure its mass, such as an electron or a proton. So since the lifetime of those particles are very, very long, so very long lifetime means very short range, actually you can measure it accurately. The uncertainty in energy is very small, meaning you can accurately measure its energy, you can accurately measure its mass. Okay. So that's the end of this lesson. So this is actually the second to the last lesson of this chapter. For the last lesson, we will try to generalize the state of the particle or the wave function of the particle.